Hello, hello. I'm so happy to have Daniel Carraway from RWDC Industries join us for a chat today. RWDC has been making waves with creating amazing products. And not just that, one of the really inspiring things has been this desire to scale. And that is something we are going to learn from Daniel, how he's looking at the products, how he's looking to scale. Thank you so much, Daniel, for joining me today, for taking the time to chat with us.
Well, thank you so much for your interest in RWDC and what we're doing. I think there's a lot of things that we have in common, and I think it's great to be able to connect and mull over ideas together. And I think out of conversations, sometimes there are some really neat things that develop out of that. So thank you for your interest and having the conversation. Looking forward to it.
Thank you, Daniel. So, as I always do, let me start with what I realize is that as we are growing up, we have numerous influences that lead us to where we are today. Would love to hear about, I knew you grew up, from my research, I saw that you grew up rural and you had a lot of nature in your life, but I would love to hear more about early impacts of packaging, if there were any, and how they influenced your work that you do today.
Yeah, I think that that rural upbringing was very influential. Um, I was really amazed as I grew up in that rural agricultural forestry, animal husbandry type setting, about the incredible things we saw in nature around us. When you're in a very rural setting, you're close to nature, you're out there every day, and just my curiosity tended to be toward natural environments. So as I began to get my formal education, I focused on plants, natural ecosystems. My interest began to move toward biochemistry and molecular biology. I was just very curious about how do plants make all these incredible materials that we use to make our lives pleasant and productive. Thinking about things like cellulose and all the carbohydrates we use from plants, fibers, plant-based oils, and these wonderful materials that we use to make coatings and paints. It's just amazing, how many natural materials are available from nature for us to use to make our lives more pleasant and productive. And so I went. I told my children sometimes maybe I stayed in school too long, but I really wanted to understand the mechanisms, at the molecular level for how all of that happens, and thinking that there would likely be opportunities to, with that understanding, work better in harmony with nature to continue to make things that we all enjoy in terms of making our lives pleasant and productive, but really do that in a way that we're not harming the environment, we're not exploiting nature, but we're working in harmony with nature to create materials and create lifestyles that then we can help people all over the world. And I really appreciate your focus on large scale, because it's sometimes it's fairly straightforward to do things in a very small scale, but how do we enable people all over the globe to benefit? So I really enjoy the aspect of making advances broadly available all over the world so that as many people as possible can benefit from it. So yeah, it's just been a real exciting, fun journey from being a child out in the forest and the fields, just with curiosity about how nature works, and then the wonderful experiences at universities to dig into the details of that, and then find a practical application. So I tell people I'm just a professional nerd. I just I just like learning things and then trying to determine, well, what's the best way to help help take the things that I've learned and make people's lives better from that.
Yeah, and you definitely have a few years over me, but very similar to you, I started a master's in biomimicry, except at your
Mm,
time it wasn't called biomimicry at all, but you were
right.
clearly early on into the thought process. Because again, as I started studying the subject, I realized everything is nature in nature is packaged and so well packaged. And again, like you said, it's using such a small part of the periodic table, and it's using such few, mostly I would say sugars and proteins, and then just
Hmm.
creating magic, which is so amazing to learn from. But similar to me, it seems I want to learn more about your career graph, because it seems that you went into pulp and paper, and that is also some a path that came to me through a hereditary situation where my father was working in pulp and paper, and I
Hmm.
joined him at one point. But would love to hear how your career progressed from your biotechnology days.
Yeah, I think that is really interesting. The pulp and paper industry has touched so many lives because a few decades ago, paper was a really important tool in what we did to communicate. And now our communication has moved more to electronic. But what we've begun to realize is that paper is a really nice material for packaging. So for food service and food packaging, the ability to make that enterprise more sustainable, better for our health and safety as humans, better for the environment. So yeah, my early career was spent with a company called International Paper, and on the fiber supply side. So I spent a lot of time trying to understand how trees made cellulose. And when you're trying to make fibers for paper, you have to remove lignin, which is a very complex biopolymer that has amazing functionality in nature. And so I ended up working with a number of really brilliant biochemists and molecular biologists. We cloned every gene in the lignin and cellulose synthesis pathways for angiosperm and gymnosperm forest trees. And that exercise enabled us to learn just a tremendous amount about the mechanisms for how that works. How do these enzymes polymerize these basic building blocks? Whether they start with carbohydrates or lipids, and just fascinating about how nature has worked all this incredible chemistry out. And there's like, wow, why can't we do that? And so learning how to do that was a lot of fun in my early days. And as I looked at this incredible, array of biopolymers that are produced in nature, and contrasting that to the types of synthetic polymers that we typically use, my belief is that we can really do a great job in improving packaging and improving other types of materials that traditionally are made with synthetic plastics, which it's really interesting how functional these synthetic plastics are in terms of their physical and mechanical properties. The engineers who built and designed those materials did an incredible job. It's just that they didn't think about end of life, and they didn't think about impact on human health and safety. And so they did what we asked them to do. They created these incredible materials that have enabled us to have applications that are really wonderful applications in packaging. However, as we use those things for 5 or 10 minutes, and then they never go away, and it's so difficult and expensive to try to recycle them. I thought there's got to be a better way. There's all these incredible materials that exist in nature. They also have these wonderful physical and mechanical properties. So how do we replace some of the materials that we're currently using with ones that are better? And I'm not one that says we shouldn't use food service items or food packaging, because think about all the incredible advances we've made in food safety and food distribution because of the plastic materials that have been developed. And we need to continue to, to handle materials in a way that's safe and makes it convenient and gives us the ability to distribute it broadly so people can benefit. We just need a different material. We need to replace the things we have been using with natural polymers that enable the same functionality, but then give us a incredibly improved scenario with regard to the health of humans and environmental health. And we want to have an end of life and a circular material flow that makes sense, as we have now. What is it, 8 billion people on the planet, and more to come. And all those people want to have pleasant and productive lives too. So let's continue to make all these wonderful advances possible and offer these great products, but let's just make them out of a natural material that then doesn't cause harm to the environment and to people. We have to be able to do that globally to really enable everyone on the planet to benefit, because there's a lot of us, and I love people, I love nature, and all the wonderful people that we have the privilege to meet in our lives. They want the same things we do. They want to enjoy a productive, pleasant life, and that's how we can really enjoy one another. Is if my focus is helping you create a pleasant and productive life, then when I look around, I'll have had a pleasant and productive life too, serving you. So doing that with the right materials and with respect and in harmony with nature is what really gets me and our team excited about what we're doing.
Super. And what you said earlier about cellulose really struck a bell, and this has been an exploration which my mind keeps going back to. If you look at these beautiful trees, most of it is just carbon sequestration through photosynthesis, and
Right.
they manage to, and of course some minerals from the earth and water, but they manage to create such wonderful trunks and dense material just by sequestering carbon. And I also hope over time it's not just materials as you talk about it, but also processes, because the only source of energy is the sun. And, there you go, there's a huge tree. Of course, nature takes a little bit of time, but apart from that, the materials it creates is quite amazing. So how long was your time with International Paper? And it's really interesting to hear that, a pulp and paper company was doing things around the biotech domain while you were there, and you were already creating materials. So how many years did you spend, and how did that transpire into the next stage of your life?
Yeah, so I spent, after I completed my PhD at the University of Georgia, I joined International Paper and was with them for a decade. So over a 10-year journey. And, my responsibility was to grow more fiber on fewer acres with the lowest possible capital input and the highest possible quality, while making all of that process sustainable. And so had a lot of fun. And really the last couple of years, I spent forming a joint venture with International Paper, a company called Monsanto, a company that at the time was called Midwest Vaco, has now gone through a couple of iterations, still a very large, pulp and paper product, forest products company, and then a New Zealand company called Fletcher Challenge. And that company today is called Arborgen, and so that technology is available publicly and embodied in improved tree stocks that serve to reforest areas all over the world. But like we were saying earlier, through that journey, I became really intrigued with biopolymers. And to your point, how do we use the processes like photosynthesis, where carbon is captured and put into all these wonderful materials that then we can use for whatever we need, whether it's cellulose or some other material.
And you also mentioned lignin. And of course, delignification is such a big part of paper making, and I know that that's a wonder material. How do you see that also evolving into something? And I know I'm completely digressing from PHA right now, but I'm just fascinated with your pulp and paper side as well. So I'm going to pivot from here. But this is my last question on pulp and paper.
Oh no, that's quite all right. My initial interest in lignin was trying to determine what is the most environmentally friendly and least costly way to remove it from cellulose. So as I began to look at lignin, which is, as you know, an incredibly complex polymer, some of the properties of lignin, started being pretty intriguing. So initially, I was trying to think, how do we get the lignin away from the cellulose? And so we worked on that problem for a while, and then added to our portfolio of things we were exploring about how to use lignin. Lignin is a wonderful waterproofing material, and it adds a lot of strength to the structure of natural plant fibers. And so we're still on the journey of exploring how lignin and lignin subunits and monomers can be used for things other than just strengthening cellulose and functioning within inside of a living tree or plant. But yeah, it was all about trying to dig into the details of the material and discover how there may be ideas that we hadn't thought of before of how we could use a natural material that, like you say, its manufacture is powered by the sun, and the carbon comes from the air, and the other materials that plants are making. So it's an incredibly interesting polymer. Um, and PHA happens to be a material that has some real nice synergies with lignin and some lignin, polymers and oligomers. So we're in our company today, we're looking at how we can help, the populations around the globe benefit from some of those synergies with PHA and lignin. So that's part of our compositional work that we do to develop these different materials.
So how do you pivot from being in a pulp and paper business and slowly getting into PHA? How did that come about? How did this idea of PHA emerge? Because it's not an easy substance, and moving from cellulose to PHA, I'm sure must have been an interesting journey. Would love to hear your side of that story.
Yeah, well, again, it's probably a pretty boring story because I was just trying to find materials that could be synergistic with cellulose in terms of making packaging and in terms of making more productivity easier to achieve in agriculture and forestry. So some of the first ideas were around organic mulches for growing, agricultural crops, growing trees. Much of the produce that we find in our local grocery stores is grown on plastic films, and those plastic films, part of the functions they serve, they do very well, but then there's just a tremendous problem with those plastic films accumulating in soils and severely degrading the productivity of those soils. And when you look around the planet, actually, there is not a lot of the surface area of the planet that are highly productive soils. And if we degrade those by using the wrong type of materials in our production, then we're really going in the wrong direction. We have seen a significant degradation across the world in terms of the productivity of agricultural regions just from using plastic mulch. So I wanted to find a way to use cellulose and lignin to achieve the same or better functionality in terms of making it possible for producers to to have a viable operation, but eliminate the use of the plastic materials that were causing such problem, after the fact. So that was really the start of the journey, and then it just blossomed into all the other things that we're working on now, which is an incredibly broad array. It ranges from agricultural mulches to surgical mask to liquid containers and coated paper packaging, all the way to personal care items, food service items, food packaging. So we're working on projects now that range from packaging for chips and snacks, all the way to surgical drapes and medical equipment. So a very interesting array of opportunities for these wonderful natural biopolymers, and it's a lot of fun for a nerd like myself who likes to get in there and understand all of the chemistry and the biology and the biochemistry to dig into that. So we have a wonderful team that we've been able to assemble, to bring all these things to the point of offering them to the marketplace in a manner that makes it really exciting and economically viable to start switching from some of the materials that functionally do a good job, but then from a human health and environmental perspective, they're just not very good choices. And switching to a material that functionally does the same job or better, and then doesn't cause any problems later on. PHA is really interesting because right now our bodies are making PHA. Right now in our liver cells, PHA is being made, and the microbes in our digestive system make PHA, and then our body uses those PHA oligomers for energy molecules. Our brains run partially on PHA, and there are many other metabolic functions that PHA plays a really key role, not only in human metabolism, but almost every living organism that you can name, there's a key part of that metabolic cycle that PHA plays a role in. And so it's a natural choice to use for articles that are connected to food or connected to packaging or other things, because it's not harmful, doesn't create microplastics, has no toxicity to any living system, because it's a natural material that is intended for use as an energy storage molecule. I tell people that we know now about microplastics the same level of information we knew in the 1950s and 60s about smoking tobacco. So you can tell from the color of my hair that I've been around the sun a few times, and I'm old enough to remember that there were actual commercials on radio and television that said, "This is the cigarette brand that doctors recommend most." And we just laugh about that because no one would imagine a physician saying, "Oh yeah, go get a Camel cigarette because that'll relax you, after dinner and before bedtime." But they didn't know back then. And then in the 50s and 60s, we began to realize that, wow, that stuff's really bad for you. It'll kill you. You should not smoke cigarettes. You should not use tobacco in that manner. And now we're seeing the same type of information develop with regard to microplastics. And so we're telling people, look, guys, we have to move away from these type of materials, especially in our food packaging and our food service and our clothing, all those areas that generate microplastics, because now we're finding that the average human on the planet has enough microplastic in our body to make a credit card. And when you think of that much plastic in your body in nanoparticle and microparticle size, and we're seeing the health impacts of that, the medical community has coined a term for that. They call it plasticosis. So if something is bad and we really don't understand it well, we just put "cosis" on the end of it. So, we know that microplastics are bad for us and they cause plasticosis. We really begin to see it from the plastics that were used in artificial joint replacements for hips and knees. And so when doctors began to have to go in and replace those, hip and joints, they would see this massive chronic inflammation around the site. And we figured out it's because of the microplastics that are shed from those inserts. And so the medical profession started trying to move away from those plastics as soon as they could. But unfortunately, we found that microplastics now are pervasive in our environment. And, 80% of the fish that we harvest have microplastics. Our water, we harvested snow from, the Himalayas and found microplastics at some of the higher, the things that we thought were pristine, high elevation sites. Oh my goodness, there's microplastics in it. And it's a bad deal. It's bad news for us in terms of health and safety. And so we need to switch to a different material. And these natural biopolymers are the obvious choice that we should make. And so we've been gathering, a lot of interest and support to make the switch, but to do it globally is an incredible job. There are, by some counts, 320 to 360 million tons of plastic produced every year. And, PHA is not a good substitute for 100% of that, but for about half of it, PHA is a wonderful replacement material. And in those single-use plastics, it's an especially good replacement. For the food service and the food packaging and the clothing that we wear and a lot of the personal care items, PHA is a really good choice. So, if you said, oh my goodness, if we had, say, 150 million tons of PHA available, think of the good we could do in terms of improving human health and safety outlook. And wow, think of the environmental benefits that would come from switching to a natural material. So it's a very daunting task to think about. How do you replace 150 million tons of material? Because over the last 90 years, we've been building up, the plastics production to meet that need. And now we need to switch to PHA. And so that's what we're excited about is, figuring out, okay, how do we got this wonderful material now. We've figured out how to use it in all these applications. Now we have to go make it globally available in really large quantities so that, people, all these 8 billion people, soon to be 10 billion, can benefit, from making that change. So it's a lot of fun, and we need to get the word out and get people working together around the world as a team to make this switch.
So you've obviously told us a lot about how PHA is to be used, but I'm going to step back because even I hardly know what PHA is. So I who spend a lot of time with materials and try and learn more and more. So it would be wonderful for our audience to, learn from you, what is PHA and how is it made, and why do you think that this is such a wondrous kind of material? So those three kind of, it would be wonderful to learn from you about those three aspects.
Yeah, that's a really good question. PHA is a natural molecule that's primarily used for energy storage. And one easy way to understand it, just from a human perspective, is that when our bodies store energy, we usually store it in the form of lipid, fat. So we think of energy storage in the human body as being fat. And a similar function is needed in all living organisms. Every living system needs some type of energy storage molecule. and in many microbes and in many plants that carry out photosynthesis, and even mammals, reptiles, PHA is a ubiquitous type of energy storage molecule. It happens to be a polymer, and it happens to be a polymer that falls into the polyester class. So PHAs are natural polyesters that primarily function in nature as energy storage molecules, but they happen to have thermoplastic properties because they are polyesters. And so what we can do is take a molecule that's made naturally primarily for energy storage, but because of its thermoplastic properties, we can make materials that are replacements for the oil-derived plastics that we're accustomed to. And there are a number of metabolic pathways by which different organisms make these PHA molecules. And we say PHA so we don't have to say polyhydroxyalkanoate. So if you wanted to have a general chemical name for the material, it's an alkanoate type chemistry that has a lot of hydroxyls and a lot of units that are polymerized. So that's why it's a polyhydroxyalkanoate, but we just call it PHA for convenience, obviously. And the way we make it, at very large scale, is that we have domesticated some microbial strains that are very efficient at making PHA. And I like to use the analogy of cattle because a lot of people are familiar with, beef and milk. And so if you wanted to be a dairy farmer and produce milk for some of the wonderful foods we eat, like I'm a big fan of ice cream, and so, dairy is important for that. If you enjoy eating pizzas, then you like cheese. And so if you want to be a dairy farmer and make milk and cheese and ice cream, you need a domesticated animal that is very productive at eating grass and turning grass into milk. And so you end up with something like a Holstein or a Jersey or a Guernsey. But if you're a beef farmer, a Holstein is not what you want, because Holsteins aren't very good at producing beef. If you're a beef farmer, you want a Black Angus or something like that. So what we've done is we haven't domesticated a dairy cow or a beef cow, but we have domesticated a microbe that makes PHA. And so with the common domestication tools that humans have used for thousands of years to either make corn or lettuce or kale, all of these materials that we use for food come from domesticated organisms, and that process typically involves breeding and selection to get those traits that we want, like a cow that produces milk or a cow that produces beef or a plant that produces soybeans or corn. We've taken those same principles, the same process, and developed a portfolio of microbial strains that make PHA, which is this natural energy storage molecule that also has thermoplastic properties. And we're all familiar with polyesters, even though we might not know that they're called polyesters. But for example, most water bottles are made of a polyester. If you've ever had a soft drink that was bottled in what we think of as a plastic bottle, that's a polyester material. Now, that's a synthetic polyester, but we can actually make those same articles out of natural polyesters that then don't persist in the environment for 500 years after we used it, for 5 minutes. So we've known about PHA since the late 1800s. There was a very curious French scientist who began to observe PHA granules and microbes, and he really, wrote some interesting scientific papers back in the 1890s to describe PHA. And then over the last little over a century, we've begun to learn more and more about PHA as a natural material, and how we can use it as really the ideal replacement for some of the plastics that we've been using for the last 100 years. But it's taken us until now to really think from a perspective of nature. How do we, rather than exploiting nature, how do we work in harmony with nature to make those natural processes work well for a large scale production of PHA, so that people all over the world can use it.
Yeah. What interests me, Daniel, is that you came from a background of celluloses, and you could have easily gone to a cellulosic films, cellophenes, and the whole NatureFlex domain, but you
Yeah.
didn't. You chose PHAs instead. So it's really intriguing for me why. What is the difference, and why not go towards alpha cellulose and make films from that, and choose PHA? Because my presumption is you would have found PHAs to be much more intriguing and things that you could probably do more with, but would love to learn about that decision.
Yeah, you really hit on the key part. You can make some really interesting films with cellulose. There's a lot of versatility in cellulose. However, it's not as versatile as PHA. There are over 150 different types of PHA that we find in nature. And for cellulose, the chemical structure of cellulose as a biopolymer doesn't have as much variety and versatility as PHA. Now, cellulose is an incredible material, and it actually works very synergistically with PHA, but cellulose does not have the range of versatility that PHA has. If you have an alpha 1,4 linkage of cellulose, of glucose, you get one thing, you get cellulose. But if you have a beta 1,6, then you get starch. And there's several different types of starch, and there are several different types of cellulose. And then you have, the subtypes. You have really microcrystalline cellulose. You have other regions of a fiber that are less crystalline, more toward amorphous. And so there is a lot of interesting variety in cellulose as a material, in starch as a material, but it's an order of magnitude less than the variety that we find in PHA, because the only monomer in cellulose and starch is glucose. But in PHA, there's over 150 different monomers that can be combined in unique ways. And so all of a sudden now you have hundreds of thousands of different materials that you can make that are still PHA, but they have different physical and mechanical properties. And so that's the reason to choose PHA, not to the exclusion of cellulose or starch, but to give us tools that are very synergistic, with the celluloses and the starches and the lignins and the other biopolymers, that we find in nature. But of all the biopolymers that are produced in nature that we've discovered so far, PHA is the most versatile, even beyond hemicelluloses and pectins and augurs and all of that. So we wanted to start at a point where we had the broadest possibility for variation, and then make those materials work synergistically with cellulose, lignin, starch, pectins, all those other type biopolymers.
And also know when we look at alpha cellulosis that the process is rather harsh and also very energy intensive. You know, the yields are like 20%.
Yeah,
If I take a
yeah.
cellulose and I have to bring it down to alpha cellulose and then again, you know, take it through the sulfate and create a film, I'm talking about less than 20% yield and using a lot of energy. And sometimes people don't realize this. They just think, oh, it's a natural material. But the amount of effort we've put in trying to convert it may be even more than plastic sometimes. And how does that, in comparison to that, how does PHA work? I know that you have mentioned that you sometimes even take burnt vegetable oil or something. So you're taking a waste product in a way. So it'll be great to get enlightened on the ideas in comparison to cellulosic film, but also on its own. You know, what is how harsh or how energy intensive is the PHA process in comparison?
Yeah, really, another really good line of information to explore. We have two routes that we use to make PHA. The one that we're commercializing first is, as you mentioned, waste oils. So there are a lot of plant-based oils that are produced around the globe, millions of tons. And what we like to do is find those materials after they've been used for either food preparation or some other use, but taking those waste oils and using them as our feedstock. Now, here's the really interesting part. When we bring in a kilogram of waste oil, whether it's from a restaurant that's cooked in the oil and now it's no longer usable for cooking food, a lot of it comes from industrial food preparation facilities. So they can use it, 2 or 3 cycles with a lot of work, but then it gets to the point where it's no longer suitable for use in food preparation, and then we can take that waste, what would otherwise be a waste material, and use it for a feedstock. So when we bring in a kilogram of that, we make a kilogram of biomass. It's a 1-to-1 conversion. Now, when we make that kilogram of biomass, about 80% of that biomass is PHA. The other 20% is about an even distribution of carbohydrates, lipids, and proteins, and that can be used as a very high value nutritional additive for animal feed. And so we have pretty close to a zero waste process where we can, 80% of the biomass we're making is the PHA, and 20% it then can go right back into the animal feed market. And whether it's poultry or pigs or cattle or you name it, it's a very good additive for the animal feed industry. So very efficient conversion process. It's not energy intense because all of the polymerization is enzymatic, and we both know how efficient nature is at designing proteins that function as chemical catalysts, and we call them enzymes. Vitamin B and vitamin C and vitamin D are just enzymes that our bodies, make and use every day to catalyze chemical reactions that need to occur. And if we become vitamin C deficient, then we have health problems. Or if we become vitamin D deficient, we just don't have those enzymes that we need. And so it's a very efficient natural process to convert that waste plant oil into the biopolyester, into the PHA. And then we have the process that we use to separate the PHA from the other 20% of the biomass that's not PHA is all water-based. So it's an aqueous type process, and we try to recover as much of that water as possible. We lose some to evaporation, but then of course that just goes back into the water cycle. So we recover about probably 85% of the water that we bring in. We recover it and recycle it, and it goes right back into the process. And so it's it's a very natural, environmentally friendly process that we use once we've been able to get this wonderful one-to-one conversion of the feedstock into the biomass. There are other routes to make. You can make PHA from sugars, from refined sugars, but rather than getting an 80% yield into the PHA, you only get about a 30% yield. And then you don't have a one-to-one conversion into the biomass. So while it is possible to do it with sugars, we believe that the oils are the better choice just because of the efficiency. And then we have another process that's at the laboratory scale now. It's probably a decade away from being viable at the industrial scale, but it's direct carbon capture. So much like plants capture CO2 directly from the atmosphere, and through photosystem 1 and photosystem 2, we call it photosynthesis, where that carbon is fixed into proteins and lipids and carbohydrates. We have a process to do the very same thing, except those carbon atoms go into PHA. So we have microbes and some other plant and fungal type organisms that are very efficient at capturing carbon as CO2 directly from the atmosphere and converting it into PHA. And we ultimately will be using that process, because then that eliminates the need for us to transport the waste cooking oil from one location to another. And we'll have a dual track. We'll be able to use the waste materials, and we'll be able to use CO2 that's just captured directly from the atmosphere. And so we like that circularity. We have a circular system now. We're using carbon that used to be CO2. It's just that currently we use plants as the intermediate to capture that CO2 from the air, turn it into a plant oil. Then that oil is used for food preparation, and then when we're done with that, then we take it, make PHA. And when we're done using the PHA, it naturally biodegrades back into CO2 in water. And so it's a really nice circular material. And what we plan to do in the future is we'll still capture CO2 directly from the atmosphere, and when PHA degrades, it'll go right back to CO2, but we'll just cut out the step that we currently use to have the plants capture the CO2 and turn it into oil, and we'll just do it directly in the I guess fairly near medium term future, probably a decade away.
That's brilliant. It's literally, I can feel my insides vibrating with joy, like the things you're talking about. One of the things that I've always so enzymes are so natural and so apt, and even when I look at delignification, it's so much better to use enzymes instead of sulfates or sodium hydroxides. But what I find is time. Time is the issue. So we can use white rot mushroom and different enzymes from there, which naturally look at lignin removal. But the batches that are needed are typically, they take time. And that's how nature works. So how did you overcome that side of it? And when you say 1:1, are you looking at it at dried basis, or how do you do it? Because I'm imagining the oil becoming into a film, but then, is it when you look at oil at a certain viscosity, or it's the remnant of when we consider it in cellulose, is it bone dried, or is it at a certain consistency? So those two technical kind of clarifications for me, please.
Yeah, good question. Yeah, we look at it on a dry weight basis. So when we bring in a kilogram of oil, that is, it doesn't have any water in it. It's just, a kilogram of oil. So on a mass to mass conversion, it's a dry weight basis on PHA. So we typically utilize our PHA at a moisture content of less than 300 parts per million. And so that's the basis of the conversion. So if you have oil that has no water, entrained or emulsified in it, it's just the fatty acids. And then you take, a kilogram of that, it turns into a kilogram of PHA that also doesn't have any water in it. It's just the polymer. And in terms of time, that is one thing about enzymes. We do everything we can to, I'll use a nerd term here for enzymes, and I'll make it simple. The pKa, we talk about pKa's as we measure the activity of certain enzymes for certain substrates. And so if an enzyme is very efficient at working on a particular substrate, we say the pKa is very high. So when we're looking for those organisms that are efficient PHA producers, the polymerization enzymes that they have very high pKa's for the monomers. So it's a very efficient process. But even at that, it takes about 72 hours for the microbes to use their enzymes to take the building blocks from the oil and convert that into the PHA. So we've designed and engineered a production module where we have 3 bioreactors, and those bioreactors are run in coordination so that when one bioreactor is finished, there's another one that's in progress and another one getting started. And so we basically cycle through those 3 bioreactors. And you've got experience in the paper industry. In the paper industry, we coined this cute little term for how we made paper, and we called it semi-continuous, because the batch digesters run as a batch, but then the paper machine runs continuously. And you never want the paper machine to shut down, but you have to load the digester with the chips, do all of your pulping, empty it, you get the cellulose ready to go in the head box. And so we've got a similar design. So we have a batch bioreactor that takes about 72 hours to cycle, and then when we take the material out of that bioreactor and go through what we call the downstream to separate the PHA from the animal feed, we want that line to run continuously, but it's fed by these 3 different bioreactors that are cycling every 72 hours. So those enzymes are very efficient for their substrates, but it still takes about 72 hours for everything to happen that we want. But it's very manageable if you just think about, again, we work in harmony with nature. We see what nature does, and then we try to design our industrial processes to work in harmony with that and deliver a material that then people all over the globe can benefit from. But it certainly has to be done at large scale.
Yeah, and as you look at like hundreds and thousands of tons, I'm imagining huge bioreactors, in place, of multiple bioreactors in place, moving in tandem to be able to do that, I'm sure. And it'll be an interesting puzzle to solve as you look for scale and moving ahead. And just in terms of technological understanding, so once you have the enzymes act on the substance, is it very similar in terms of how do you convert? And by similar, I was going to say cellulose, but I'll park the cellulose just so that it doesn't become very boring. But in terms of converting it to film, how does that happen once you have the reaction having taken place?
Yeah, so once the reaction has occurred and we purify the PHA, the films that we make are usually combinations of 2 or more different types of PHAs. So if we want a film that's very soft and flexible and has a lot of elongation, that would be one combination of different PHAs. And if we want another film that's more of a rigid, a little bit less flexible, a little tougher, that would be different sets of PHAs. But once we have the PHAs, we combine them into what we call a resin. And from that point, the film conversion is exactly like is done with plastics. So the same equipment, the same processes. We even make the PHA resin into little pellets that are identical to the type of plastic pellets that the converter would make. Because it's very important, if you want to do something at large scale, to make the material work with the existing installed base of capital equipment. If we had this wonderful new PHA resin, but it couldn't be run on the installed equipment base around the world, it would be very difficult, because converters can't afford to recapitalize their entire operation. So if you went into a large film producer and saw them making PHA films, it would look just like if they were making a polypropylene or polyethylene or polyester film, because we enable this new wonderful material to run on exactly the same equipment that they already have installed.
Yeah, and we say as well, like if you're disrupting the product, don't try and disrupt everything. You keep the
Right.
same supply chain and you disrupt
Yeah.
the product, and then it can move into the same cycle, and you're not cannibalizing anybody's market as well in many ways. So this really takes me towards the usages, and I know you mentioned in passing some of the usages. How do you see, and of course, once it's a pellet, it can be used in multiple ways. And what do you think are the best usages for the material? And I, of course, see on your website numerous different usages. What are you most excited about, at least in the near term?
Yeah, so in the near term, we see food service, food packaging, apparel, so different textiles, and then non-wovens for personal care items. So things like, hygienic wipes, baby wipes, feminine care products, baby diapers, non-wovens that are used in, the medical field. And then, of course, food service items like, cups and lids and straws and cutlery, food packaging films, takeout containers, all the things that are used in convenience in some societies, but then equally focused on necessities. Some societies don't, they don't focus as much on convenience items as some of the more Western economies, what we tend to call the more highly developed Western type economies. But they're equally important critical materials from a personal care, from consumer goods, even just from safety in terms of food distribution, that we want to focus on, in all over the globe. So that's why food packaging is such a important focus. That's why apparel is such an important focus, because most of the microplastics that are causing us problems come from apparel, from the clothes that we wear, and everything can't be made of cotton. But PHA does work very synergistically with cotton. So these, going back to natural materials for our clothing, whether it's PHA or cotton, or some other natural fiber, we think will go a long way toward, helping with the microplastics problem. And we have some really exciting fabrics that over the next few years will be coming to the market from some exciting brand owners who are really working hard to get away from the microplastic generating materials that are currently used in clothing. So some really exciting things going on there. So clothing and food, those are two of the biggest necessities that a human has regardless of where you live. And so we want to focus on that first. And then, when you get beyond those real basic necessities of food and clothing and shelter, to some degree, then we can get into more of the, the convenience and and the other type items. But personal care comes really close behind that as well. So food and food packaging, food distribution, clothing, and then personal care items. So those are the big three areas where we're focused.
And that's extremely versatile. When I look at the kind of products, one is a yarn and the other is a non-woven, like again a yarn but a different kind of polymer. And then of course, it's a extrusion process when you look at a food focus. So it's a wide variety of usages, and that's really exciting. One of the things you referred to earlier, and I'm really excited to learn about, is that you mentioned flexible films. And that I feel is such a huge challenge. And we don't talk about it enough because, of course, it's again human ingenuity to be able to block moisture and air for such a long time. And, you rip open a bag of potato chips after 6 months and it feels like it was made like an hour back. It's that fresh
Yeah.
in terms of smell and the crispiness. But of course, you and I know that's going to probably stay for 1,000,000 years, not even 500 years or whatever they say, because it's so beautifully designed. But like you said before, end of use or end of life is not really planned. And it was really nice to hear you talk about the possibility of using PHAs for a shelf life application or an application where there is barriers. How do you see that, and how would you ideally engineer that application?
Yeah, so for those very high barrier applications, PHA can be an important component, but PHA by itself does not have the physical and mechanical property performance envelope that would enable a really long shelf life, high barrier material. PHA is actually pretty good as an oxygen barrier. It's among the best, but it's average in terms of a water vapor barrier. Now, for liquid water, it's an outstandingly good barrier, but for water vapor, it's about the same level as PET. So, PET is used as a beverage packaging material, and it's okay. It's not good enough to use for long shelf life. Like, when you open your bag of chips, you want them to be crunchy. And if you made a bag with just PET or just PHA, after about 3 months, it wouldn't be crunchy anymore. So what we have developed are some really exciting other biopolymers. They happen to be carbohydrate polymers that work incredibly synergistically with PHA to replace the type of petroleum-derived barriers that we have now, along with aluminum. Most of our high barrier packaging today is vapor deposited aluminum, and it's deposited on a substrate that's usually a petroleum derived material. So we have an exciting new class of polymers that function as good as or better than aluminum for the vapor barrier. And when you deposit aluminum on a film, it's a very expensive process. The good thing about aluminum is that it's infinitely recyclable, but the bad thing about it is once it's put into a multi-layer structure in a chip bag, it's not economical to recycle it anymore. And so what we want to do is replace aluminum as a barrier material in these multi-layer packaging applications. You cannot do it just with PHA alone, but to make a multi-layer structure of a biodegradable PHA with a biodegradable carbohydrate-based polymer, both are natural materials. We find them in nature. They don't cause any harm to humans or other, any other type of life form. They biodegrade naturally and go right back into the carbon cycle. So we have a number of things in our pipeline. PHA is the one that gets the most attention because it's so exciting and versatile, but we also have to have other materials that can work with PHA. There's no one single material that's the magic solution for everything. You have to have a lot of different materials that can work synergistically with each other. And that's the same whether it's a synthetic material or a natural material. And so what we try to do is when our customers have a problem they want us to work on, we have a big portfolio of these natural materials that we can work with to create a solution. And in the case of vapor barrier, moisture vapor barrier, and long shelf life, high barrier packaging, it takes PHA plus some of these other materials to get the solution. But they can still be natural materials that don't harm people or the environment.
And what happens when you talk about a metallized film and the amount of, if you're vapor metallizing, it's pretty low levels of, 1 or 2 nanometer kind of levels of aluminum. What happens if you're just putting it back in soil? Does it demineralize? Does it stay? How does that work? Is it a compostable substance or a biodegradable substance even after metallization, even if it's not recyclable?
You can, if you have like you say, if you've got maybe 2 or 3 angstroms thick of a vapor deposit metal, it's not a lot of material on a mass basis. So you could think about if you metallized a PHA film, then that certainly would be compostable, and it would be either industrial compostable or home compostable. The aluminum is going to still be aluminum, but there's not much of it there. And you just have to think long term. If I am putting a lot of aluminum on a per mass basis in a small area, eventually I'm going to have accumulation of aluminum. It might take a long time. So we think the better solution is to go with materials that don't bioaccumulate. They go right back to the carbon cycle. They go right back to the water cycle or the nitrogen cycle. So we really like the idea of circularity. To make aluminum a circular material, you have to go collect it and take it back and refine it and recycle it again. And if you're making a beverage can, that's pretty easy to do. But if you're vapor depositing it on a biodegradable film, it's incredibly difficult and far too expensive and complex to go and collect it and take it back to the source. Aluminum is again a very versatile material. A lot of good things about aluminum. It's just probably not the best choice for high barrier packaging. It's what works now. We've learned how to vapor deposit aluminum onto films, and for the foreseeable future, there's going to be that vapor deposited aluminum in a lot of these multi-layer high barrier packages. But over the next decade or so, I expect we'll have better solutions with some of these natural materials than aluminum in terms of performance and in terms of circularity and end-of-life options.
Guess what, Daniel? We've been speaking for almost an hour and 10 minutes, and we haven't even talked about RWDC.
Yeah.
It's been that exciting. So it's kudos to you and your knowledge and the excitement that you bring into the conversation. So I would love to pivot and talk about RWDC, how it came about, what does the company do, and how is it planning to scale? So, just the ideas around your wonderful company.
Well, yeah, thank you for that. So RWDC is really focused on improving people's lives. We want to make people's lives better. And the way we think we can do that is by providing materials that are safe, they don't cause problems with human health or for the environment. And so we're focused on these natural materials to do that. And like we've mentioned several times, we want to be available globally. And we've borrowed the concept from the quick serve restaurant industry in terms of having distributed manufacturing that's modular in nature. So here in the southeastern part of the United States where I live, we have a really fun food provider. They're called Chick-fil-A. So everyone likes Chick-fil-A sandwiches, and they're a great organization. And if Chick-fil-A wants to sell more chicken sandwiches, they just go on the other side of town and build another production module. They know exactly what it looks like, and whether it's in, Montana or in Georgia, when you walk into a Chick-fil-A restaurant, or more commonly, you go through the drive-through, you know exactly what to expect, and the processes for making the Chick-fil-A sandwich are the same. And so what we've done is we've said, hey, let's take this idea of a quick serve restaurant franchise, and let's modularize the production process so that we can very efficiently replicate it globally. And we'd build a sub-assembly and then take those sub-assemblies to a production site and put them together and very efficiently, very rapidly expand our capacity, because we want to have a very light ecological footprint in our manufacturing operations. And so by distributing our manufacturing across many different sites globally, we can have, zero ecological impact. We can actually improve the ecology of different areas and very rapidly scale up our manufacturing. So that's probably one of the biggest differences in RWDC and some of the other, biopolymer or even other polymer operations. Usually you see these large, massive industrial chemical complexes, that are put in place to make these materials. There's a company called BASF, and they have what they call the world's largest industrial chemical complex in Ludwigshafen in Germany, and it's right along the river, and it's like 7 kilometers long and 4 kilometers wide. It's this massive complex, and they make a lot of materials there. But what we would rather do is have, a small ecological footprint, have manufacturing distributed around the world, and have it in a way that it's not complex. It can be scaled very rapidly and economically to get these materials, into the hands of people where they can really, improve people's lives and work and do it in harmony with nature. So just a different way to think about it that we think is worth considering, and our partners and our investors seem to agree with us that that's a good approach to take.
And you seem to have mastered the art of being able to raise money. Is that because it's just such a convincing technology, and they have huge trust in what you're trying to do? How does one go about it? Because I know that a lot of listeners here are people who are startups trying to build businesses around bioproducts. What would your advice be? How should one approach that, and how should one, and maybe the kind of investors that we should look for?
Mm-hmm. Yeah, I wish I could say I had mastered the art of raising money. We have very, very thankfully, and I'm really grateful to our investors that have provided the dollars that we've needed to do this. We haven't raised a lot of money, but we've, since we started the company, we've raised about $200 million that we've put to work in terms of getting to the point we are now. We still have more money that we need to raise, but we're nearing the end of our journey for where we need to raise equity, and moving closer to the point where we can expand with debt capital and with cash that we generate in the business. But we're actually in the process of another capital raise now that will probably be our last or next to last. And what we've found to be to create interest with investors is, of course, there needs to be a compelling benefit to humans in some way. And what we have found is that our focus on making people's lives better, having an offering that improves people's health and the health of the environment is a very compelling narrative. There's so much focus on the need to have better environmental performance now that it's well recognized by the market and by brand owners. What we've chosen to do is focus on large global brand owners because that's where we feel like we can make rapid impact. It's probably much more difficult to focus on individual consumers in the early stages. So my advice would be to, position your product in a way that you can interest these large global brand owners, because let's use a company like Kimberly-Clark or PepsiCo, for example. They are going to understand more about individual consumer behavior and individual consumer needs than I will ever understand, because that's their business, and they've been in business for over 100 years serving the needs of individual consumers, and they are really, really good at that. A very large apparel brand, for example, and we could pick any one from a Patagonia to a Lululemon, whatever apparel brand is sexy at the time. They've really invested tremendous resources and time understanding how to interact with individual consumers. And so as a startup, as a very young company, RWDC is about 5 years old now. The kind of effort that it would take to be able to be effective with individual consumers, that's decades and decades of investment. And so what we've chosen to do is partner with these large global brand owners and make sure that we really thoroughly understand their needs. We understand the directions they want to go in. We understand the problems they're trying to solve. And then we build a solution for them that makes their life easy. We want our brand owner customers to be heroes to the individual consumers that they're serving. And so, if I can make you the hero to your customers and create all that value for your brand and for your customers, then you're naturally going to think of me as a provider that can help you with what you need. There's a saying that I borrowed from an individual who was he grew up in the door-to-door cookware sales business, and I can't imagine a more difficult task to sell cookware door to door. And he grew up in the 50s and 60s and 70s. His name is Zig Ziglar, and he developed into a motivational speaker, and he went around helping people understand how to interact with individuals. And he had this one saying that really made sense to me, and he would say, you can have anything in life you want if you'll help enough other people get what they want. And so that's what we do with our brand owner customers. We try to understand what they want, what they need, what's going to create value for them, and then we figure out how to get it for them and do it in a way where we can have fun together, and we enable, a lot of value creation while we're enjoying working with each other and having fun. And if I'm focused on serving your needs, then I'm eventually going to get my needs met as well. So I think that the really important things when you're raising money, and you're trying to think about how to deliver a message to an investor or a customer, is figure out what it is they need. What is it that they want? And then create an offering that meets that need or that want. And then you'll capture their attention. And then your responsibility is to deliver on the things that you've said you will provide to them. And we have found that to be something that's enabled us, to be able to get the capital that we've needed at each stage. And again, I won't say that we're experts, and we certainly haven't mastered it. And currently, the environment is very difficult economically in terms of raising money. But because we do focus so much on our customers' needs, our investors' needs, we deliver things that we say we'll deliver. We're not perfect by any means. We have struggles and difficulties and delays and missteps just like anyone else. But we always communicate those things very clearly. We explain what's happened, why it's happened, and what we're doing next. But it's just that when your investors and your customers feel comfortable that you really are doing everything possible to serve them and meet their needs, that's what we have found to help us, be in a position to be able to raise capital that's needed to serve them at a larger scale, and in a broader array of applications.
You are a very wise man, Daniel Carraway. But and two things actually in your business model that actually really are apparent for me. One, and these are lessons for me actually. One is work on base products and then distribute them, and the second is look for scale. Those are two very strong takeaways that I'm getting from you. And again, two questions from that. Where does that fire in the belly come from to, look at this? You're talking about, starting a company 5 years back, raising over 250 million. And now you're talking about raising $1 billion, as I hear when you talk to Robert Downey Jr. And then looking at global presence. So where does that fire in the belly come from, and what is it that you're seeking in the stage of your life and what you want to leave behind?
Yeah, that's a really, really good question. You're full of good questions. We need to talk more often because I learned so much, from the insights that are contained in your questions as well. And that's what makes it fun, to get together and talk about these things. So, really, my desire is just to see people's lives improved. I love people. When you look around your surroundings, the only thing that is long term and lasts forever is people and your relationships, and so I guess just being a little nerd that grew up out in agricultural, it was that close community where we helped each other out. Something about being in an environment that there weren't, as many people around, and you needed to help your neighbors. Maybe that was part of the genesis of it. But just wanting to see people have pleasant and productive lives, and then propagate that as broadly as possible. That's the part of it. Of course, all of us at an individual level, we operate in our own self-interest. That's just part of who we are as humans. But I think we have to be careful to make sure that we don't let our self-interest encroach on others' self-interest. So, the things that I enjoy and the things that I want, are important to me, and they may be different than the things that you want and the things that are important to you, but that doesn't mean they have to be exclusive. I can help you achieve the things that you want and have fun together doing it, and then, I can get the things I want too. So really, for me, I don't really care about a legacy for Daniel Carraway. What I care about is a legacy for your children and your grandchildren, and a society that can have peace and harmony and pleasant existence. And if there's some little part we can do by providing materials that can bring people together for a broader good for everyone, that just maybe I'm just weird, and that's just part of being a nerd, but that's just exciting to me to use science and nature to see that happen. and it just it's very satisfying when you can see something that you've invested a lot of effort in along with your team, and then as a team we can enjoy seeing that positively impact society at large. So it sounds kind of hokey, I guess, but that's really the basis of it. Is improving people's lives and seeing us use nature the way it's intended to be. Let's work in harmony with nature and each other to make things better. And it's an exciting journey because it's not easy, and there's so many problems along the way. But part of the fun is when we have these big challenges and problems to get a team together and say, hey, Ved, what do you think about this? What if we did this? And you might say, well, have you thought about this? And just the fun of exchanging those ideas and benefiting from the insight of your team it's just so much fun, and it's really an exciting to me when we have these kinds of problems that we can work on together. So having a great team around you, enjoying an accomplishment that you worked on together. Unfortunately, humans have been at war with each other, and you hear these things about, oh, when you're in the war together or when you're in the trenches together. And I think there's something to that. Not that we certainly don't need to be warring with each other, but when we're working together on a problem that's really important and really can have a big impact on people's lives, I think that's the thing that that I really enjoy and gravitate toward. And we've got some big problems with human health and safety because of plastic materials, and we've got some big environmental problems because we've been addicted to plastic, and we just need to change the materials that we're using. Let's continue to have those wonderful, valuable applications, like all the nice apparel and the non-woven materials that go into medical uses, and the food packaging and the food distribution. Straws are not evil. They're very useful, and some people actually need straws. If you're a paraplegic and you want to get liquid into your body, a straw is a necessity. So straws are not evil. Let's just don't make them from polypropylene anymore. Let's make them from a natural material that will serve the purpose just as well, and then not harm the individual or the environment. So those are the kind of things that are fun to work on.
And that is absolutely beautiful to hear. And sadly, all good things have to come to an end. And I'm looking at the time here, and I've taken so much of your time, and you've been so gracious. But I have to ask this one question, and this kind of blends in well with what you were talking about. What does the idea of good garbage mean to you?
Oh, I think that's we could probably talk another couple of hours on that. But I think, to me, good garbage is, when we have materials that have provided a lot of value in their initial application, that we have ways we can take those materials and use them for another application. And to me, it's the circularity is, sure, maybe we call it garbage, but it's good garbage if then we can put it in some kind of circular process where those materials don't become harmful, where they don't interfere with the function of our environmental systems, and they don't cause harm to human health. So I think the circularity conversation is a good one to have, and if we can think about that when we're designing materials and articles, then we would have all good garbage.
Thank you. Thank you so much, Daniel, for sparing your time and sharing your wisdom with us. And I really look forward to seeing all these materials. There's so many questions that remain with me, but I will hold that for another conversation, because we look at PHA, and we've been familiar with PHA for a while, but yes, availability, cost, those are the challenges right now. And I think what you're working on is going to change that, because, as materials get available, it will be more cost effective, and it is going to change the world. So thank you for working on that, and thank you for serving humanity in such a wonderful way, and thank you for sharing all your wisdom with us. Thank you for being on the show.
Well, it's my pleasure, and thank you for having us. I look forward to hopefully being able to talk more.